Okay, in this video we are going to prove a statement related to homeomorphic graph. So statement reads as follows: if two graphs G1 with n1 vertices and m1 edges and G2 on n2 vertices and m2 edges are homeomorphic, okay, then we have this relation between the vertices and edges of G1 and G2. Okay, so that says then n1 plus m2, okay, we sum up the number of vertices in G1 and edges in m2, and that will be equal to the number of vertices in n2 and the number of edges in m1. Okay, so let's go and prove this statement. Okay, so we are given that G1 and G2 are homeomorphic. So by the definition of homeomorphic graphs, okay, we can see that, okay, G1 and G2, okay, so let suppose that G1 and G2 are obtained from G, okay, by a sequence of elementary operations. Okay, and let G1 is obtained from G by, say, R elementary operations. And G2 is obtained from G by, say, K elementary operations. Okay, so when we perform an elementary operation, what we do is something like this. We consider an edge UV, say X, okay, then we delete that edge from the graph, okay, then we insert a new vertex W and we insert these two edges UW and UV. Okay, so that says, okay, after doing an elementary transformation on a graph, the number of vertices will get increased by 1. Okay, so we add this new vertex W, so number of vertices in the graph, this graph, will get increased by 1, and the number of edges will also get increased by 1. Okay, we replace this edge by 2 edges, so number of edges will get increased by 1. Okay, so that says, so okay, in G1, okay, we can see that, so G1 is obtained from G, okay, so by R elementary transformation. So that says this n1, which is the number of vertices in G1, so n1 will be equal to the number of vertices in G plus R. So here we have performed R elementary operations, and number of edges in G1, it will be the number of edges in G plus R. Okay, so that is what we saw here. When we perform an elementary operation, number of vertices will get increased by 1 because we add this new vertex and we replace one edge by 2 edges. Okay, so if we perform R elementary operation, then number of vertices in G1 will be equal to number of vertices in G plus R, and number of edges in G1 will be equal to number of edges in G plus R, and similarly here also the same kind of thing happens. Okay, so that says if you look at the other graph, so this is for graph G1. Similarly, if you look at graph G2, the number of vertices, okay, it will be equal to the number of vertices in our original graph G plus, so here we are performing k operations, plus k, and the number of edges, m1 is number of edges in G plus k. Okay, so in this case we can see that, say, if we add this is not m1, sorry for that, m2. Okay, so we are looking for this thing, this condition, but n1 plus m2. Okay, so let's add these two together, n1 plus m2. So n1 plus m2 is nothing but, okay, cardinality of the vertex set of G plus R plus cardinality of the edges in G plus k. Okay, so here we are solving for k and R. Okay, so here this says R is nothing but m1 minus the number of edges in G, and if you look here, this from this we have k is equal to n2 minus number of vertices in G. Okay, substituting R and k here, we get this will be like number of vertices in G plus, so R is nothing but m1 minus the number of edges, the cardinality of the edge set of G plus the cardinality of the edge set of G plus k. K is nothing but n2 minus the cardinality of the vertex set of G. Okay, so here we can see that okay, this will cancel with this one, and okay, these two will cancel, and we have m1 plus n2. Okay, and that's it, that's the proof. So here we can see that n1 plus m2 is equal to m1 plus n2, n1 plus m2 equal to n2 plus m1. Okay, so that says if you have to graph G1 and G2 with this G1 with n1 vertices and m1 edges, and G2 with n2 vertices and m2 edges, and if they are homomorphic, then n1 plus m2 is equal to n2 plus m1.